Hello everyone. Today I will present a paper called Improving Robustness to Model Inversion Attacks through the Mutual Information Regularization. And this paper focuses on MI attacks, model inversion attack, which is a type of privacy attacks aimed to reconstructing the input associated with any given model output. For example, in this face recognition model, the attack goal is to recover a representative image for. Sorry. Okay, sorry for that. For example, in this model, in this face recognition model, the attack goal is to recover representative like this kind image for some targeted identity or targeted label Bob here based on access to the targeted model. Moreover, and the authority may have some auxiliary knowledge that can boost or facilitate the inference. Possible auxiliary knowledge could include or could be some cropped or blurred face images. And the access to this target model can be either white box or black box. In the white box setting, the adversary has a complete knowledge of the target model. And where in the black box, the attacker can only query the model. The model inversion attacks can perform on different models, for example, linear regression, decision tree, and neural network. The common algorithm is to output the feature that is mostly like to produce the target label under the target network by, for example, by computing the MLE of this conditional probability. And it can recover the sensitive attributes for not only training data, but also testing data drawn independently from the domain distribution. Existing defense mechanism against MI attacks includes two threads. One thread is called the model-specific defenses. That's they study like studies the model-specific heuristics to mitigate the attacks. It study like for example for decision tree, it considers the relationship between the sensitive feature depths in the tree and the model susceptibility. So sorry, the model's susceptibility to ML attacks and provide the guidance to place the sensitive feature in the tree. And this is a method proposed in this paper. And for the DNN, some papers focus on like inject some uniform noise to the confidence score, and also some paper consider like reduce their precision. Another strategy is try to focus on generic defense strategy that can be applied to any models. For an example of this strategy is train a differentially private machine learning model. However, the previous work has empirically shows that the DP cannot provide protection against the MI attacks with a reasonable model utility. And this paper presents a theoretical analysis that can explain the efficacy of the differential privacy. And also this paper, the proposed defense method is model agnostic and effective for both black box or white box setting. So this for this example, for the face recognition example, like these two, and both the recovery, the training image or the testing image would incur the privacy loss to the target label, right? Because these two are both belong to a same gap. So it is important to design a defense method to ensure the privacy of the entire training distribution instead of just the members in the training set. So a naive defense is to produce a classifier where the prediction, the model, the output distribution y height is independent from the input distribution x, and in this case, the adversary cannot learn anything about the input data distribution for given output label. However, this classifier could clearly be used in practice because the model not learn anything. And so how to limit the dependence between the model input distribution x and the output distribution y height to prevent the adversary from inferring the training data distribution associated with a specific label. So the idea here is to quantify the dependence between the x and the y height using their mutual information, and incorporated this mutual information into the training objective as a regularizer.
I have a quick question here. For the black box model, definitely, the only thing you know is you can only query the model, right? So the only thing you know is the output. How about for the white box model? Do they know anything related to the intermediate updates or? Anything,
they know the model. They know the model parameter. They know they just like download the pre-trained model, just like that one. Because like for example, your like TensorFlow, I think there is some like or model do. They have a lot of models trained by some data, and then you can download that and do some analysis yourself locally.
Yeah, but for that case, do you think that intuition is strong enough to protect the model inversion attack? Because this one only try to say separate make the output distribution and the input distribution independent, right? So if I know some intermediate value, is that possible? I can still inference the input distribution, x distribution.
Yes, because actually you no. For that one, you don't know the data. Like go back to this part. Like for example, the white box. The difference for white box, they know the target model, right? That model is already trained. That means if you have an input, then you can have the intermediate like the feature map. But the final target model is just a function, right? On parameters like y equals to ax plus b something. This one you know the a and you know this function, and you can feed this image to this one and get the intermediate feature map, just like that. That's what you say, like the intermediate updates. It's actually not. Actually it's not in the training process. What we talk about is the attacker can know the training process of the target model, right? That is your case. What you want to say? But that is for the practice, or like in the practice, like people do the white box. It's just like I have trained a model based on my local data, and I release the model. Yeah, that's that. I release the function, and then you know what is a. That's like that. It's not like there is a paper like a Mochon read paper is they try to share some like the intermediate layer to the server or something, I remember, and to perturb the feature map. Is that this is different. This is not kind of that is in the training process. In here, this white box, the model, the target model, you can know the parameters, but you don't know the input image, and so you don't know the input or the intermediate updates. You don't know that.
Okay, so the target model is already known, right?
Yeah, that's yeah. Maybe you can choose like you can say it's you can treat it as inference phases. Inference phase.
Yeah, it's already trained. It's already known. So here we're talking about the inference process, right?
Yes.
Okay. Okay.
And I mean, the white box is considered like the inference physics, but here we try to how to generate a good model so that even you do the inference physics and the correlation between the input distribution and output distribution somehow is independent. That is the defense method for this paper. And for example, like this is this is a loss function, and here this part, the first part here, this part is the original loss function for the main prediction task, and the lambda here is a coefficient term that try to control the trade-off between the privacy and the utility. This part is privacy utility, and this part is the mutual information between the input and the prediction equal to this one, because this is like a integral formula, and to deconstruct of the this regularizer, and we can rewrite in this formula. This part is the entropy of the prediction. This is actually the entropy of this conditional probability. And if the final model F is a deterministic model, this term will be 0. That means yeah, this is very intuitive, right? Because like if F is a deterministic model, for example, y equals to ax plus b, or y equals ax given a same x, or we know the y output is the same. That means this entropy here is 0, and also this part will introduce this regular mutual information will only have hy hat here. It introduce this is attributed model ultimate distribution, right? And when the F is sorry, this is stochastic. This a typo here. When F is stochastic, the regularizer will additionally promote the uncertainty of the model output for a fixed input hy x1. That means the model, the regularizer not only have this part but also have this part. And in practice, reducing this entropy of the prediction will encourage the model output to be encourage the model output to be more concentrated, and so that the different input to be mapped into the same or the very similar output. And also increasing this part, this entropy makes the output to have a large variance for given input x. And both this term will make the input x less likely to be determined from y hat here. In general, the computing the mutual information is computationally expensive. It requires model. It requires modeling the joint distribution of the model input and output, and taking the integral over the domain, over both domains, right? And which is impractical for most of the relative real-world prediction tasks. So this paper presents some like efficient method to implement the proposed method for different machine learning models. And for example, like a linear regression, decision tree, and neural networks. And these three models have been successfully taxed by previous works. And the basic idea is to find the approximation to the mutual information regularizer. And for example, here is a linear regression, and this is a model y equals to a times x, and because like this model is deterministic, and the mutual information only is reduced to hy here, and they propose to use some approximation based on this paper. Sorry, they try to first approximate the distribution of the y height by a Gaussian mixture like this one. They build a distribution here, and then use some like approximation method to get the mutual information. for like this is a method here. We can see like it can be easily calculated. The other one is the model is they consider how to modify the decision tree and to use this proposed attack method or defense method. And they consider the decision tree model or algorithm called ID3, which is the most classic algorithm for training decision trees. And this decision tree, for example, here you can see here is some tables, and here is different features, and this is the classes for in fact or not in fact. And your like decision tree will put this kind of feature, this feature x1, x2, x3, and in different different leaf node or row node, and try to predict whether given a feature, given a row, what is the prediction for these classes. And this specific process, and the algorithm begins with some original set as the root node, and on each iteration of the algorithm, it iterates through every and use the attributes of the set and calculate the information gain of each feature, and it then selects the attributes that have that has the largest information gain value, and then split the train data set into a subset using that feature, and make a distinction train node using that feature, and repeat this process many times. And yeah, and the case is since the distinction tree method is also the decision tree trained with this method is also deterministic. The mutual information reduced to the entropy of the prediction. To defend that kind of attack, ML attacks, they add like entropy system to the splitting criteria. That means they don't. That means they select the feature not only based on maximum information gain, also have to have this parameter. Try to find the features based on this new new criteria. And the other model is they consider deep neural network. They try to find some like a tractable approximation for neural network. This paper using the line of work on information bottleneck and regarding the neural network as a Markov chain. That means like for existing Markov chain of neural network, and Y is the ground truth label, actually the feature. Z is the stochastic encoding of the input acts as some intermediate layer. And for example, we can like this one. And Y hat is a prediction. And the first part, and by using some like data processing inequality, like what this one, the entropy of X and the prediction is smaller than X, and the intermediate layer or the stochastic encoding Z, and they have a new training loss like this one, and theta is a model parameter and includes the two terms. The first part is to learn Z is intermediate layer, and Y is prediction. This part is try to learn an encoding that is maximally maximally informative about the ground truth label, and measure the prediction performance of the model. This part is try to learn a good model, and this part is to reduce the dependence between the X and Y height by minimizing the upper bound, like ZX, and improving the robustness of against the ML attacks. This is like a new routine loss function, and this loss function can be used the variational method to solve. And this is the evaluation baselines. They consider many attack algorithms and defense baselines. And they consider for attack algorithms, they consider like 4 algorithms. One is first called MIP. This is in this method, the MI attacks is treated as an optimization problem that seeks for the maximum posterior probability estimate of the sensitive attributes under the detected model. And the second one is called knowledge alignment. It's trying to train an inversion model that swaps the input and output of detected model using the dataset drawn from distribution, similar to the previous data distribution. And the inversion model is used to reconstruct the input feature for a given target model input. And the update lakes model is trying to change the inversion, the utilization of the inversion model by leveraging the generative adversary network to improve the reconstruction accuracy. And the GMI here, GMI solves the MAP to recover the most possible private attributes through the gradual descent. And the key idea of the GMI is to leverage the public data to learn a generic prayer for the private training data distribution and use it to regularize the optimization problem underlying the attack. And there are some existing defense baselines available for specific models and attacks. For example, like a differential priority, and also the other one, and also the noise confidence scores for black box DNS. That means add some uniform noise to the confidence score or the prediction result of the model prediction. And this one is for decision tree, and which adjusts the depth of the sensitive features. And it shows like it's called priority. That means they adjust the depth of the sensitive attributes, and some paper shows that the different depths of sensitive feature will affect the attack accuracy, or will affect the attack accuracy. And this is our overall setting of this paper. For this is black box, but it includes black box setting and the white box setting. And attacks include knife, MAP, and also knowledge alignment and model update leaks and MAP with counts. What is this for white box? What is this with counts? With counts because they consider they have some auxiliary knowledge, like the numbers of training samples for each classes. And the previous paper shows that with this kind of counts, it can this kind of auxiliary knowledge, the attack performance will increase. And also the GMI here, and also focus on different models, three models, and different data sets, and how they consider different baselines. And for example, DP, ADA, SSP only for linear regression, and priority for decision tree, and DPSGD for neural networks. And they consider utility matrix and attacker matrix, and for example accuracy. What is accuracy here? The accuracy is the attacker accuracy. It's the first after they use this kind of attack model, they can recover some image, like image given some labels, and they train a classifier to see whether the image can be recognized as the target class or not, to compute the attack accuracy. And how there is a ECE, I will introduce this ECE after. And this is the result. This is figures compare the performance of the proposed defense against the baselines on different black box setting, include MAP, naive for MAP, knowledge alignment, and update leaks. And we can see this figure shows that this MID here, this green one, right? Training and testing stuff, and this is the DP, and this is DB and the priority here. And we can see that MID, the proposed method called MID, consistently achieve a better utility and privacy trade-off than the differential privacy for protecting against the MI attacks. For the decision tree here, we can see some like a model specific defense strategy, like the priority, like you can see the purple one here, which we can see the problem here. This purple one, we can see that the MID can is more robust than priority in most cases, expect when the model have very high performance. This part F1 score is more than 0.57. Now but like priority has its own drawbacks. For example, it can only apply to the decision tree, and also it can only protect a subset of attributes instead of other attributes or all the attributes. Overall, like we can see the proposed defense can significantly improve the model robustness for any fixed model performance. This part is the model performance. We can see is much more robustness, right? And this part we consider the model calibration metric. Model calibration is the degree. Is a degree to which a model predicts the probability, estimates the true correctness of likelihood. And one metric is called expected calibration error. That is measure the difference between the model accuracy and the confidence, and which is important for evaluating a risk model. And we can see these two figures, like this error is smaller is better. And we can see that MID mostly achieve the significant lower ECE error than the differential privacy for given a robustness level, for given robustness level attack accuracy. And the next method is for the next result is for the white box MI attacks, and they consider like a GMI, which is the state-of-art attack against the neural networks, and MIP with cons. There's only known attack against the decision tree, and we can see from these results like the MID can outperform differential privacy by a large margin to defend against the white box MI attacks. And also I can see this part like the priority is better than the MID in somewhere F1 score. Yeah, that's the same phenomena appears in like in the black box method. And this part is the reconstructed image of MID and differential privacy. We can, and this is no difference. This is a target model, and we can see that the MID can block attack much more better than differential privacy somehow, like on this one, for this one, and the reconstruction of differential privacy can still retain some like facial features of the target individual, while the reconstruction for the MID are mostly completely different from the target individual. Yeah, for example, this is they have classes, eyeglasses. And also like after introduce this kind of results, you can see like some one common observation is the attack performance is very close on training and testing data set. For example, consider these two and these two green one. This is one is training, one testing, and this red one is training, one testing. And for this one is testing, and also this part, right? And the attack performance is very close on training and testing set. This is implies that the model inversion attacks can pose similar private threat regardless whether an individual data is selected from the training or not. And also in this experiment, things like the MID and the differential policy can help mitigate the overfitting. The private threat of MI attacks is presented to the population of the training instead of the training set only. And also like based on the experiment result, we can see the differential policy is not good, and it's the reason. But like we know that some like the definition differential policy shows that different model can prevent any kind of attacks. The reason, so we should know why, right? So this paper gives some like theoretical analysis. They give a formula for the MI attacks. Also, for example, they formulate the MI attacks and quantify its distributional privacy loss. And unlike the privacy works that capture the privacy loss of the members in the training data, this paper they consider the modeling the privacy loss of the members in the population instead of only the training data set. And these MI attacks can be included like into these steps, and this is a thematic model inversion game played between the server and the adversary. And these attack setting are more to simplify this the model inversion settings. They consider they let the input image the input features or the input random variable. Consider like the sensitive attributes, non-sensitive part, and the labels. And also they can the server send the model and non-sensitive features and labels to the adversary, and adversary gets the sensitive features based on the knowledge of the adversary, and the adversary wins if the guess for X as the sensitive attribute correct. And through this game, we can get the model inversion attack privacy loss. Things like how many times of the adversary or what the probability of the adversary winning. And more specifically, like they have this kind of experiment for MI attacks. For example, the server draws a training set S through a distribution and a training classifier F. M here is the model. Sorry, I'll introduce these 4 words. A is the adversary, M is a learning algorithm, P is a distribution. For example, here distribution, and tau is property function that maps the sensitive attribute. That maps sensitive attribute into the property of the interest of the attacker. And the server draws a data sample V from a distribution P, and given the F, X, and S as a non-sensitive attributes, and labeled the adversary A, the adversary output A, X, and S, Y here, and output this value. And if this value equals to the tau X S, and this equation equals to 1, and otherwise equals 0, and the gain of the game evaluated as this formula, yeah, this formula, this probability, right? And the best strategy for the adversary is to sample the sensitive attributes through this conditional probability, and we can get the best gain of this game equal to this one. Since like after this one, this is the adversary game, we should have in order to measure the adversary advantage again from the classifier F. They defined an alternative for underlying distribution Pxs and Pxny here, and so that Xs the sensitive the sensitive distribution data set and the non-sensitive data set have no correlation with each other. With this, that means the sample the Xs from a new distribution right here, and finally they have the previous laws defined by these two gain together. These two gain, this is this gain, and this one is alternative gain to get the adversary advantage. And I know this is definition for different policy. We familiar with this one. That's by like for example this one. The output model is the difference of model is difference bounded by e to the power epsilon. No matter like given D and D prime, that is that's the adjacent similar adjacent data set, and which can provide different policy like the machine model. So they build indistinguishability for the DP model, distributed game. And for example, this includes 4 steps. The first one is the server choose a B from using uniformly at random equals 0 or 1 randomly, and the server draw a training set as from distribution if B is 0 and or from the alternative distribution if B equals 1, and the server chain classifier using the learning algorithm and present the F to the adversary, and the adversary output the B prime, and if the B equals B prime and the output is 1, otherwise equals 0, and the gain of the in this game can be equal is equal to this one, and they have a theorem for like this one. This theorem shows that the game with a thematic model inversion game can be upper bounded in terms of the best possible gain of in the distinguishability game. Like for this is the formula here, and to mitigate the threat of the model inversion attacks, and they treat this one. They require this term to be not much greater than 0.5, and so the result, they also have a learning algorithm to show that when the learning algorithm is using data differential policy, the MI privacy loss is tightly upper bounded by this formula. This formula N here is a training data, and we can see like in order to make this bound small, we need to set the epsilon as like 1 divided by training data, like a big O here, and in this case, the privacy value is too small to allow any useful computation. This is the conclusion. This paper proposed a defense against model inversion attacks based on regularizing the mutual information between the model input and prediction. And this paper also presents a trackable approximation to the regularizer for linear regression, decision tree, and neural network. And this paper also provides theoretical analysis for common observation that DP cannot defend against ML attacks with a reasonable model utility. Yeah, that's also some references. Any questions?